Today we are talking about Noetherianity up to Symmetry. So I'm Azhar Farooq, a PhD student at Technology University of Eindhoven. So first we recall Noetherian rings. A commutative ring R is called Noetherian if every ideal of R is finitely generated, which means that there exist finitely many elements f1, f2 up to fm in the ring R such that they generate the ideal I. Examples of Noetherian rings, for example, all finite rings are Noetherians, every field is a Noetherian ring, and then the ring of integers is a Noetherian ring. In fact, this is a principal ideal domain, means every ideal is generated by exactly one element. And then one of the mostly used Noetherian ring is the polynomial ring in n variables over a field K. Some properties of Noetherian rings. So if we fix a ring R, polynomial ring in n variables, then every ascending chain of ideals stabilizes. Means if we have a chain of ideals I1 which is contained in the ideal I2 which is contained in the ideal 3 and so on, this chain stabilizes means there exists some capital N such that In is same as In plus 1. Another property of the polynomial ring is that every ideal of R has a finite free resolution. This is a particular case of a very famous theorem, Hilbert's CZG theorem, which says that every finitely generated module over the polynomial ring R has a finite free resolution. And if I is a graded ideal, then the Hilbert series, which is defined in this way, is a rational function which can be written in this way, where f of t is a polynomial with integer coefficients, and here d represents the dimension of the quotient ring. Here dimension means the Krull dimension, and the value of f at 1 gives us the degree of the ideal I. So now we see some of the non-Noetherian rings. Noetherian rings are nice, we have seen in the previous slide, but not all rings are Noetherian. For example, the polynomial ring in infinitely many variables is not a Noetherian ring. Indeed, the ideal generated by all the variables is not a finitely generated ideal. A motivating question could be that how far is this ring from being a Noetherian ring? And its answer is given by Noetherianity up to Symmetry. In the next few slides, we will see what do we mean by Noetherianity up to Symmetry. Let's collect some observations. First, we will see in some sense the ideal generated by all the variables is finitely generated. Let sim n be the symmetry group on n letters. Then we define the infinite symmetry group sim infinite as the union of all the finite symmetry groups. And then this sim infinite, the infinite symmetry group, acts on the polynomial ring Pn by permuting the variables. For example, if we have a permutation pi, then it acts on a variable, then it actually acts on the indices. For example, if we have a permutation that maps 1 to 2, when it will act on a variable x1, it will give us x2. And similarly, when this permutation acts on the variable x2, it gives us x1. And for other variables xj, when j is not is equal to 1 and 2, then it gives us same answer, x of j. It fixes all other variables. Then in this sense, this ideal generated by all the variables, it's actually generated by only one sim-infinite orbit, x1. I means that the orbit of x1 under the sim-infinite group gives us all of the variables x1, x2, up to so on. In this sense, the ideal generated by all the variables is actually generated by x1 up to symmetry. So in this sense, we said that this ideal is finitely generated. Some more observations. An ideal I of the polynomial ring in infinitely many variables is called sim-infinite stable if when we apply a permutation on an element in I, then pi of f should be again in the ideal I for all permutations pi and for all f in the ideal I. Thus, we saw an example of a sim-infinite stable ideal that is finitely generated up to symmetry. Means the ideal generated by all the variables x1, x2, this one. This is a sim-stable ideal and it is finitely generated up to symmetry. And one might ask whether this was an accident. Let's consider one more example. The ideal J that is generated by all square-free quadratic monomials. Here is a typing mistake that here this inequality is a strict inequality. I is strictly less than J. Then this ideal is a sim-infinite stable ideal, and we can see that this ideal is generated up to symmetry by the orbit of x1, x2. Any other monomial in this generating set can be obtained by applying a permutation on the monomial x1 times x2. We fix a positive integer c and we consider slightly more general polynomial ring which we denote by p sub c times n. This is a polynomial ring with the coefficients coming from a field and its variables are indexed by two indices I, j, where I runs between the numbers 1 and c and j runs over the natural numbers. A variable in this ring actually can be visualized as a matrix with c rows and infinitely many columns. One can write like x11, xc1, then x12, xc2, xc2, and so on. This is a matrix with 0 and capital N columns. So this is a C time infinite matrix. This is how we can visualize the variables in this polynomial ring. Then the symmetric group sim infinite acts on this polynomial ring by permuting the columns. Means a permutation acts only on the second index. For example, if we have a permutation 1, 2, when it will act on this the set of variables, then it will permute the column. It will map. We have columns like this one. Then it will swap these two columns. Column 1 will be replaced by column 2 and vice versa, and it will fix all other columns. And general problem in this area is to study the sim infinite stable ideal of the ring, and contributions to get answer are due to Cohen, Hiller and Sullivan, Darisma and Cutler, Sam, Snowden, Nagpal, Church, Ellenberg, Ferb, and many others. And one of the fundamental theorem in this field is that every sim-infinite stable ideal I of the polynomial ring is finitely generated up to symmetry. Means there exist polynomials f1, f2 up to fm in the ideal such that the ideal I is generated by the orbits of this polynomial, where this notation shows that where we are considering the orbits of all these polynomials. In this sense, the ring PCN is called Noetherian up to symmetry. That is, every sim-infinite stable ideal is generated by finitely many sim-infinite orbits.